So, with that little prelude, let us come back to this uncountably infinite dimensional space of functions on the real line, in which case we can generalize. So, we can generalize the notion of a dot product or inner product between two functions. Essentially, if I take two functions x and y both on the variable t, that dot product is not going to be a summation anymore, but an integral. So, x t y bar t dt. Taking that idea further of multiplying corresponding coordinates, and instead of summing, you now integrate. So, the integral replaces the operation of summation here. Now, of course, it is easy to verify, and I leave that as an exercise to you, the properties of linearity and the commutativity and so on. So, I leave it to you as an exercise here, verify the properties of conjugate commutativity. In other words, if I interchange the order of the arguments, there is a complex conjugation involved. Second, of linearity in the first argument. So, if I take a linear combination of two vectors or two functions in the first argument, then the corresponding inner products are also similarly linearly combined. And third, positive definiteness. So, I leave this to you as an exercise. But what I wish to emphasize at this point is the famed Parsevals theorem, of which we are aware in the context of the Fourier transform. So, let me recapitulate that very important theorem in the context of the Fourier transform, and let us also give an interpretation to it. You see, the Parsevals theorem as we know it for continuous functions says that if x t has the Fourier transform, now I am going to use the frequency Hertz frequency variable. So, this is the Hertz frequency variable nu. In other words, what I mean by that is that the Fourier transform of x t is essentially integral x t e raised to the power j 2 pi nu t dt integrated over all time t. So, this is the Hertz frequency variable in Hertz. Recall that you can also have an angular frequency variable. So, for example, you could write x cap of omega. Now, I will use this capital omega when we are talking about continuous time. We are going to follow some notions of different notation for continuous time and discrete time. So, we will use this as the angular frequency variable for continuous time. In which case x cap omega is x of t e raised to the power minus j omega t dt. And there is a simple relation between capital omega and nu. Omega is 2 pi nu, angular frequency and Hertz frequency. Well, simple things, but we should put down all our cards in the beginning, so we do not get confused later. Now, again, this is a little bit of abuse of notation. because I am using x cap of capital omega here and I am using x cap of nu there. And depending on the context, I must interpret either Hertz frequency in the argument or angular frequency in radians per second in the argument. Normally, from the context it shall be clear, and if there is some confusion likely, we will make it clear by explicit statement. But remember that from the context we should be clear whether we are dealing with Hertz frequency or angular frequency, radians per second. Anyway, with these details, let us come back to the Parsevals theorem. What does the Parsevals theorem say? The Parsevals theorem says the following: if you have the Fourier transforms of x and y, so if x t has the Fourier transform, let us use the Hertz frequency variable x cap nu, and y t has the Fourier transform y cap nu. This arrow denotes the Fourier transform. Then there is an equivalence of the Fourier transform inner product and the time inner product. That is what the Parsevals theorem says in our language now. So, the inner product in time, so to speak, is equal to the inner product in frequency. In other words, if you take x cap and y cap and construct their inner product in the same way, treating the frequency as the independent variable or the argument, now this is a very beautiful and a very powerful interpretation of the Parsevals theorem. When we talk about the inner product perspective, we have a very different way of looking at Parsevals theorem. And in fact, if we really think of it a little more deeply, Parsevals theorem becomes so much more intuitive when we talk in terms of inner products. And let me take a minute now to show you why it is so intuitive. Indeed, what Parsevals theorem says in the language of inner products is this, and let us do the same in 2 dimensions and then it will be absolutely amply clear. So, I have 2 vectors, let us call them x and y. Now, what Parsevals theorem says is x dot y is independent of the coordinate system, simple enough. What coordinate system we choose to represent x and y does not affect the inner product. That is what Parsevals theorem says in a way. And to strengthen, you see, it may not be obvious to you why Parsevals theorem relates to this statement. It is obvious for 2 dimensional vectors that the inner product is, or the dot product is independent of the coordinate system. What is not obvious is why is this related to the Parsevals theorem? Well, towards that we need to go back to what x cap nu really is in a way, and that will become clear if we write down the inverse Fourier transform. So, we can write down x t in terms of the inverse Fourier transform as x cap nu e raised to the power j nu t d nu. Nu is the Hertz frequency variable again. So, in a way what we are saying is we are reconstructing x t from its components. each of the x cap nu for different values of nu is a component here, and this is the way we have reconstructed x t from its components. And in reconstruction, we have used these vectors. Each of the e raised to the power j nu t is like a vector, is a function of the real axis. The only catch is e raised to the power j nu t is not an L2R function. So, we have to deviate a little bit there from our discussion, but if we choose to ignore that fact, we have essentially taken these coordinates, multiplied them by the corresponding so called functions along each of the coordinates nu and added them to get the function x t. So, each of the x cap nu is like a different expression of the same vector x in a different coordinate system. So, what we are saying in Parsevals theorem is that the dot product is independent of the coordinate system. Whether we choose to use the standard coordinate system of time to represent the function or the slightly less obvious coordinate system of frequency to represent the same function, the dot product remains the same. So, these and some other such interpretations are what are offered when we represent functions in terms of vectors, or when we think of functions as generalizations of the ideas of vectors. And now, for the last remark in this lecture, which we shall build on even greater in depth in the next, namely, what is the connection between functions and sequences, continuous functions and sequences. Just to initiate the discussion here without completing it or rather taking it further, we shall do in the next lecture. But just to initiate the discussion, let us go back to the idea of piecewise constant approximation. So, suppose we have this piecewise constant approximation of this function on intervals of length 1. So, I take the standard unit intervals and I make a piecewise constant representation of a function. So, I have this. So, let the values be, let us say c minus 1 here, c 0 there, c 1 there, and so on and so forth. Now, it is very easy to see that if I take the basic function phi t described this way, 1 between 0 and 1 and 0 elsewhere, then this piecewise constant representation can be written as c minus 1 among other terms phi t plus 1 plus c 0 phi t plus c 1 phi t minus 1 and what have you afterwards. So, to conclude just this introduction of this correspondence, we can note that equivalent to this piecewise constant representation that I have here, this function in V 0 that we talked about last time, equivalent to that function is the set of values c minus 1, c 0, c 1 and so on. So, the sequence c n, n over all the integers is equivalent to that piecewise constant function in V 0. Any of them can be constructed from the other. From that piecewise constant function, we can construct the sequence. From the sequence, we can construct the piecewise constant function given phi t. Now, this equivalence is what we shall take further and delve into deeper in the next lecture. And in the next lecture, we shall also build further these ideas of vectors, functions and sequences. Thank you.